Okay, so let's look at a couple of examples that get a little bit more difficult where you start combining several rules at once. So here we've got a function g of t, so we get t as the variable this time, and here's the definition. So you've got g of t is this t minus 2 over 2t plus 1, that entire fraction, all raised to the power of 9. So this is definitely going to be a chain rule application. However, one thing you notice is that the inside function itself is a fraction. So when we go to differentiate the inside function, which we will have to do at some point, we're going to have to use the quotient rule. So this is a combination of the quotient rule and the chain rule. And that doesn't need to be something that gets confusing as long as you go carefully, go slowly, take it one step at a time, and stay organized. That's really what it comes down to. And as long as you do that, it doesn't matter how complicated things get. You can just slowly grind through them one step at a time. And that's really what you're shooting for, is to get that kind of confidence. But for now, let's look at this one. So how are we going to start this one? Well, let's apply the same kind of strategy as we did before. Let's really identify with a bubble what the inside function is, right? We've got some function of t raised to the power of 9. That's how you should think about this. So when we differentiate the outside function, we can just say, well, the derivative of the outside function, if we leave the inside function alone, is just going to be 9 times that inside function of t, so t minus 2 over 2t plus 1, all raised to the power of 8, right? Where this is that same inside function. If we just draw a bubble around this one just so they can be, your eyes can match them up, right? So that's the derivative of the outside function, but the inside function has been left unchanged. So we still have to multiply by the derivative of the inside function, because that's what the chain rule says. So I'm going to add that in after. So we've got t minus 2 over 2t plus 1, but I'm just going to stick a prime on the outside of that, because we still have to take its derivative. So that's just the application of the chain rule, but now you can see that to work this derivative out, well, we're going to have to do the quotient rule. So why don't we actually do that as a separate calculation? So here it is. Let me just draw a line here to keep things separate so it's a little easier to see what belongs to what. Let's work this quotient rule calculation out. So we've got t minus 2 over 2t plus 1, and we want to take the derivative of that function. So we're going to get, well, remember the formula, we've got the derivative of the numerator times the bottom, or the denominator, unchanged. So times 2t plus 1. Then we're going to subtract the numerator, left alone. Don't take its derivative, but then you do take the derivative of the denominator. So that's the quotient rule. But, okay, of course, we have to also divide by the square of the denominator. So that is the quotient rule application. So now let's finish this off. Because t minus 2, if you take its derivative, you're just going to get 1. So the derivative of this function is just 1. So we're just going to have 2t plus 1 minus what? Then we'll have t minus 2, that'll go here, times the derivative of 2t plus 1. What's the derivative of 2t plus 1? Well, derivative of 2t is just going to be 2. Derivative of 1 is going to be 0. So that this derivative is just going to work out to be 2. So why don't we write the 2 in front? So we'll write this as minus 2 times t minus 2. And then all of this can be divided by, well, the denominator is not going to change because we didn't do anything with that. Okay, so now let's expand everything in the numerator. Might as well clean this up now before we plug it back into our main thread over here. So this is going to, let's expand everything out. You get 2t plus 1 minus 2t plus 4, right? If I multiply the negative 2 into the brackets, I'll get negative 2t plus 4. So that's all over 2t plus 1 squared. So now you can see, okay, there's a cancellation that happens. The 2 t's cancel and you just get 1 plus 4. So you finally end up getting 5 over 2t plus 1 all squared. So that is what you get for this derivative. So now let's put this back in and we can finish our main problem here. So we get 9. And hey, actually, before I go any further, notice that when we put this 5 over 2t plus 1 squared, this is a power of 2t plus 1 that's gonna show up in the denominator down here. We also have 2t plus 1 over here, which really since it's part of a fraction that's raised to the power of 8, there's actually, if I split this up, we can actually combine the denominators. So I'll show you what I mean by that. So what I'm going to do is I'm just going to split this fraction up because it's raised to the power of 8. So I can write this as t minus 2 to the power of 8 divided by 2t plus 1 to the power of 8, just using properties of fractions. So it's worth doing that because then now when we put this fraction in for the derivative, we're going to get multiplied by 5 times 2t plus 1 squared. Then it's easier to combine these and condense it as much as possible. Multiply the constants together. 5 times 9, that's 45. So your numerator is just going to be 45 times t minus 2 raised to the power of 8, all divided by 2t plus 1 raised to the power of 10. And that is your g prime of t. So just as a recap, the first step we just did the chain rule application, right? Took the derivative of the outside, left the inside function alone. That's what this first part is here. Then afterwards we multiplied by the derivative of the inside function. But that required the quotient rule because it's a fraction. So that's what we worked out over here. And then from there we just put the pieces together and simplified as much as we could, and we ended up with this.